Now student, we are going to discuss this question number 13.16. Clear? In this question it is given to you, suppose we think of fission of 26 iron 56 nucleus into two equal fragments. Clear? And that is given to you 13 aluminium 28. Okay. Is the fission energetically possible? And some value of that is the atomic mass unit are given to you. Clear? So any reaction is, or the fission process is energetic possible or not, we can calculate by using Q value. If we are getting Q value that is positive, at that time we can say this is possible, and if we are getting Q value negative, it means this is not possible. Clear? So now fully concentrate. Now we can see, if we write this equation, so from this equation you can say this is 26 Fe, that is 56. Clear? Now it is breaking into, now this is 13 aluminium, that is 28, plus now we can say this is 13 aluminium 28. Clear? And let's suppose, definitely we have to calculate this Q value. So initially I am assuming, let's suppose Q is this side, that is on the product side. So for that one, first we will calculate mass defect. Clear? So mass defect is given by, that is mass of reactant minus mass of, that is product. Clear? So now you can see, if I am talking about mass of reactant, clear, mass of reactant, we can see that is mass of this nuclei of 26, that is Fe, and this one is 56 minus. Clear? How can we write mass of product? Mass of product, that is mass of nuclei, that is 13 aluminium, that is 28. Clear? Then, and we can write like this, minus, again this is mass of nuclei, that is 13 aluminium, this is 28. Clear? Then we can see this one. Now you can say, actually we need mass of this nuclei, and directly you can say that is the atomic mass units are given to you. It means we have to subtract mass of an electron. Clear? How can we subtract? In this reactant side we have 26 proton, means 26 electrons, 13 electron in the product, this is 13 electrons. So definitely I can say mass of electron, it will be cancelled out. Clear? So directly I am writing this mass is the same mass as AMU in the atomic mass unit. So directly you can say this value you have 55.93494 minus, what about mass of nuclei? So mass of nuclei, it is given to you 27 point, that is 9819. Clear? And that is 1 minus, now because we are having same, so we can write like this, 27.98191. Clear? So now if you calculate, you can write like this, that is delta M. Clear? Yes. So now I am writing like this, delta M, this should be equal to, clear, delta M, this should be equal to that is 55.9349, 55.93, that is 494 minus. Clear? Now if you add it, you can write that is 2, this is last, in the last we have 2, 9 we have 18, we have 1, so 1. Clear? We can say that is equal to 3. Clear? Then 8 or 8, that is 16, we have 1, so that is we can say that is 10, and this one is 19. Clear? Now we have 1, so 8 and 7, that is 15. Clear? We have 1, so 3 plus 2, this is equal to 5. Clear? That we are getting. Clear? So directly if you observe, you can see we are getting this value 0 0 dot, directly we can say that is 0. Clear? Let's suppose I am taking up to this one. Clear? So in the last we have 12 minus 4, that is 8, 7 or this one, so from that one we can say that is equal to 8. Clear? So we have 2, this is again we have 8, and that is what 5, that is equal to 2. Clear? And this one is 0, but my dear student, we are getting this value negative. Clear? It means now you can say you are getting this mass defect, that is negative. When this is negative, it means I can say mass of reactant, it will be more compared to mass of product. Clear? So if I calculate Q value is given by delta MC square or you can write like this, any negative value, clear, multiplied with 931.5 million electron volt. So definitely my observation is you are getting this Q value that is negative. So it means we can say energetically this reaction is not possible, clear. So now you can say if you want to process this reaction, at that time we have to provide some energy to this iron nuclei, and after that it will be converted into two same nuclei of aluminium, clear. Yes, so this is all about this question, clear. Now student, we are going to discuss this question number 13.17, clear. In this question it is given to you, the fission properties of 94Pu 239 are very similar to those of 92 uranium 235. The average energy released per fission is 180 million electron volt. How much energy in million electron volt is released if all the atoms of 1 kilogram of pure 94Pu 239 undergo fission, clear. So now let us try to understand. First of all, concentrate on this nuclei. Now can we say for 239 gram, we have total number of atoms that is present in the in this nuclei, that is equal to Avogadro number, yes or no, because this is equal to 1 mole, clear. So from that one we can write like this, for 1 gram we have, that is Na divided by 239, clear. This is Na divided by 239. So now we can say, because we are talking about 1 kilogram, so it means we can say 4000 gram. Now we can say what is total number of atoms that is present. So Na divided by 239, and this will be multiplied with 1000, clear. So from that one we can write it like this, this is equal to 6.023 into 10 to the power 23 divided by, this is 239, clear, and multiplied with, that is 1000, clear. So 6.023 into 10 to the power 23 divided by 239 multiplied with 1000, clear. So now we can say, now this is the number of atoms that is present, clear. So can we calculate it? Yes, definitely you can write like this, 6.023, that is divided by 239, and it will be multiplied with 10 to the power 26, clear. So now you can do, this is near about, let's suppose this is 250, so this will be near about 2 point something, yes or no, clear. So number of atoms in 1 kilogram of pure 94Pu, that is 239, it is equal to, now if you solve it you will find this value 2.54 into 10 to the power 24 atoms, clear. Yes, so in this question it is given to you, the average energy released per fission is 180 million electron volt, clear. So can we calculate total energy released, because this is our objective, clear. So total energy released, this is given by, we can say 180 million electron volt per atoms. Now what is the total number of atoms that we have? This is equal to 2.54 into 10 to the power 24 atoms in 1 kilogram of pure nuclei, clear. So now we can see this is multiplied with 2.54 multiply 10 to the power 24, clear. So this is what we can say, that is atoms. So now we can say this one and this one, that is cancelled out, clear. So now we are talking about total energy released, clear. So total energy released, this one is given by, total energy released, this one is given by that is equal to 180 into 2.54 into 10 to the power 24, and this is in a million electron volt, clear. So now if you solve it you will find this value 4.54 into 10 to the power 26, clear. 4.54 10 to the power 26 million electron volt. So now we can say for 1 kilogram of pure that is the 239 pu, we can see the number that is the total amount of energy that is released, this is equal to this figure. Clear everyone? So this is all about this question. Now student, we are going to discuss question number 13.18, and in this question it is given to you a 1000 megawatt fission reactor consumes half of its fuel in 5 years. Clear? So now we can see, let's suppose I am assuming initial mass of fuel, that is equal to, let's suppose that is equal to m naught. Clear to you? This is equal to m naught. So according to this given question, this fuel remains from m naught to m naught divided by 2 in the time that is equal to 5 years. Clear to everyone? This fuel remains from m naught to m naught by 2 in a 5 year. So a 1000 megawatt fission reactor consumes half of its fuel in 5 years. Okay, how much 92 uranium 235 did it contains initially? Clear? So it means my objective in this question is to find value of m naught. Clear? This is my objective. Clear? Assume that the reactor operates at 80% of its efficiency. Fine. Then all the energy generated arises from fission of 92 uranium 235, and this nuclide is consumed only by the fission process. Clear? So actually, how can we solve this problem? First of all, let us try to understand this strategy. If you talk about this 92 uranium 235, so if we talk about, that is the energy per nuclei, if we talk about, you can say this will be near about 200 million electron volt. Definitely this data you should keep in mind. Clear? So now we can say energy of each that is the, you can say energy of each atom, you can say that is equal to 200 million electron volt. Why I am writing energy of each atom? Because I am assuming in each atom we have one nuclei. Clear? So energy of each nuclei, you can say that is 200 million electron volt. So we can convert this million electron volt into joules by 200 into multiply 10 to the power 6 multiply 1.6 into 10 to the power minus 19, and this is joule. Clear? So from that one we can write like this, 1.6 into 200 into 10 to the power minus, and we can say this is equal to 13 joule. Clear everyone? So now if you say, actually you are getting this value energy per atom. Clear? Now can we find total number of atoms that is present in 1 kilogram of uranium? Yes. How? Actually you can say in 235 uranium, you can write like this, in 235 gram, we can say number of atoms that is present, it is equal to Avogadro number. Clear? So if I am talking about 1 gram, so in the 1 gram we have Na, that is divided by 235. Clear? So now if I am talking about 1 kilogram, this is equal to 1000 gram. So for the 1000 gram number of atoms that is present, Na divided by 235 into this is 1000. Clear everyone? So now it means I can write like this, number of atoms per kilogram. Can we write it? This is equal to 6.023 into 10 to the power 23 divided by this is 235 into that is 10 to the power 3. Clear? So from that one we can get the total number of atoms per kilogram. Clear? So can we calculate it? Yes. So you can write, this is what? This is number of atoms per kilogram. But actually what is my objective? My objective is to find the total energy that is present per kilogram. So for that one you can say, if we multiply this value with this value, you can say atom and atom that is cancelled out, and you will get this value joule per kilogram. Clear? So now we can say energy per kilogram. Clear? Energy per kilogram, you can write it like this, this is 1.6 into 200. Clear? And it is multiplied with 10 to the power minus 13. This is joule per atom. This atom cancelled out. So 6.023 into 10 to the power 23 divided by, that is 235 multiply 10 to the power 3. Clear? Yes or no? And definitely you will get this value in joule per kilogram. Clear? Yes or no? Now, if we find what is the total amount of that is the energy that is generated, because total half of the fuel is consumed, so I can say total energy generated, total energy generated, and total energy generated, this one is given by m by 2 multiply we can say that is equal to 320 into 10 to the power minus 3 multiply 6.023 divide by 235 into 10 to the power 26. Clear everyone? Now you can say this total energy generated, this will be equal to what? Clear? We can write like this, this whatever this one, that is m by 2 multiply, now we can say 320 divide by 10 to the power 3 multiply this is 6.023 divide by 235 into 10 to the power 26. Clear? And this should be equal to, now we can say that is power multiply time. Clear? So one more thing is given to you, this reactor is operating only for 80% of time, so you can write like this, this is 80 by 100 and multiplied with power. Actually this reactor is for 1000 megawatt, so 1000 and that is multiplied with 10 to the power 6. Clear? And now we can see this is equal to P multiply T. So time is given to you, that is 5 here. So directly you can say 5 multiply. In 1 year we have 365 days, 24 hours and 3600 seconds. Clear? Definitely slightly we have a calculation, definitely we have to do some calculation. So now if you solve all these value, you will find that approximate value of this m naught, this will be near about, I am saying near about 3076 kilogram. Definitely there is some calculation you have to do, but I think process is clear to everyone, that first of all you have to write like this, you have to find energy of each atom. Clear? After that you can find that energy per kilogram. How can you find? For that one you have to calculate number of atoms per kilogram. After that if you multiply it with mass, you will find total energy generated, and this total energy generated, it should be equal to power multiply time, and this is for 80% of efficiency. So if you calculate, you will find this value of m naught, and this should be equal to 3076 kilogram. Clear to everyone? So this is all about this question. Now student, we are going to discuss question number 13.19. Clear? In this question it is given to you, how long can an electric lamp of 100 watt be kept glowing by the fusion of 2 kilogram of deuterium? Clear? So again a very interesting question we have, because we have a bulb of 100 watt and 2 kilogram of deuterium is given to you. At what time you can glow this bulb continuously? And definitely you can say, sir, we have only 2 kilogram of deuterium. Clear? How much energy it can provide? Let's try to understand that a 100 watt bulb can be glow for what time. Clear? So now concentrate. One reaction is given to you, 1H2 plus 1H2, this should be actually product is going to be happen, that is twice He3 plus 1 neutron, and energy that is releasing 3.27 million electron volt. Clear? So from that one you can say, if you are talking about two nuclei, we can say that is 1H2, it is releasing total amount of energy 3.27 million electron volt. Clear? So from that one can we find energy per atom, because we are assuming in one atom we have one nuclei. So energy per atom we can calculate 3.27 divided by 2, this is in million electron volt. Can we convert this into joules? Yes. So now 3.27 divided by 2 into million means 10 to the power 6, electron volt we can convert 1.6 into 10 to the power minus 19 joule. Clear? So now if you multiply it, you can write like this, 3.27 into 10 to the power minus 13, it is 16 divided by 10 and 1 by 2. Now we can say that is equal to 8. Clear? And we are getting this value in term of joule. Clear? So now 8 multiply 3.27 into 10 to the power minus 14. clear. 8 multiply 3.27 into 10 to the power minus 14 joule, clear. So now if you multiply it, clear, you can write like this: 8 6 we have 50, 8 7 we have 56, so this one is 5, 8 2 that is 16, we have 21, so that is 2, so 24 we can say that is 26, clear, into 10 to the power minus 14 joule, clear. So 26.16 into 10 to the power minus 14 joule, this is actual energy that is releasing, clear to everyone? Yes. So from here can we find the total number of atoms that is present in 2 kilogram of deuterium? Yes, actually you can say in deuterium we have 2 gram, and in the 2 gram means we are talking about we can say 1 mole. 1 mole means we can say total number of atom that is present equal to Avogadro number. So for 1 gram we can write it like this, that is Na divided by 2, clear. So definitely if I am talking about 2000, that is the 2000 gram. So for the 2000 gram number of atoms present, in 2000 gram number of atoms that is present, Na divided by 2, and this is 2000. So from that one we can say that is equal to 1000, clear. So now I can say number of atoms present in 2 kilogram, that is deuterium, 2 kilogram deuterium, and this should be equal to 6.023 into 10 to the power 23 into 10 to the power 3, clear. So from that one you can write it like this: 6.023 into 10 to the power 6 atoms. Yes or no? Clear. So this much amount of atom that is present in 2 kilogram of deuterium, clear to everyone? Yes. So now you can see, can we find the total energy that is developed or generated, clear. So I can write total energy, clear. So total energy, you can see this is actually energy per atom, yes or no? And you can say this is what total energy per you can say in the total number of atom in 2 kilograms. So total energy generated, this is equal to 26.16 into 10 to the power minus 14, clear. 26.16 into 10 to the power minus 14 multiply 6.023 into 10 to the power, we can say that is 6, that is 26, clear. This is 26, clear. Yes. So now if you multiply it, you can write it like this: 26.16 into 6.02 multiply 10 to the power, that is 12, clear. So if you multiply it, you will find this value near about 1.576 into 10 to the power 14 joule, clear. So this is total amount of energy that is generated by 2 kilogram of deuterium, clear to everyone? Yes. Now actually we know one formula, and that formula we have, that is power. Power is actually denoted by P, and this should be equal to W by T, clear. Now already it is given we have to glow a bulb that is having power 1000 watt, clear. So time T, we can say that is W by P, clear. W we have, that is 1.576 into 10 to the power 14, and it is divided by, what about power? Power is given to you, that is equal to 100, clear. Now you can say this is what joule per second, and this is what joule. So from here can we find the total time taken up to which this bulb can glow? Yes. So now we can write like this: 1.576 into 10 to the power 14, and it is divided by 100. So this is 10 to the power 12, clear. So now I am getting 1.576 into 10 to the power 12, and that is second, clear everyone. So this is all about, that is the time T, clear. But better if we convert this into number of years, then let's see that how many years we can glow this bulb from only 2 kilogram of deuterium, clear. So we can write like this: total time 1.576 into 10 to the power 12, this is in second. So first we can convert this second into number of hours, clear, then number of days, clear. So that is the number of days, then we can say number of years. So you have to divide with 365 also, clear. So now if you calculate it, clear, you will find this value near about 49962 years, Clear? So this is a very interesting figure. Yes, my dear student, only from 2 kilogram of deuterium you can glow a bulb for 499, almost 50,000 years if the bulb is having watt, that is 1000 watt. Now let's think about that energy source. Let's suppose, because in today's scenario we are talking about LEDs, we are talking about CFLs that is having a power of 11 watt, 10 watt, 5 watt only, and LEDs is only for maximum 2 watt, 1.6 watt, and we are talking about 100 watt, and 100 watt bulb is glowing for 50,000 years. So now you can calculate that for how long we can glow our LEDs CFL. So that's why we can say this nuclear energy is a vast source of energy. Clear everyone? If we produce energy in a very systematic manner or in a synchronized manner, actually this is a very sufficient source of energy. Clear? So what is the answer of this question? Answer of this question we have, that is 50,000 years. So this is all about this question. Nowadays student, we are going to discuss question number 13.20. Clear? In this question it is given to you, calculate the height of potential barrier for a head-on collision of two deuterons. Now you can say, sir, what is this potential barrier? So hint is also given to you in this question. The height of the potential barrier is given by Coulomb's repulsion force between the two deuterons when they just touch each other. Clear? And we have to assume that they can be taken as a hard sphere of radius 2 Fermi. Now actually let's suppose we have two deuterons and two deuterons are at infinity. Now let's suppose we are bringing these two deuterons near to each other, and let's suppose we are touching. Definitely when we bring these two deuterons near to each other, definitely a repulsive force will also act. So whenever we are bringing them at a certain distance, we have to do some work against the repulsive force. Clear? And actually that work is stored as a potential energy. So overall, if you want to calculate that energy or that potential barrier, it means we have to find potential energy. So now you can see, let's suppose I am assuming this is, let's suppose one deuteron. Clear? And let's suppose this is another one. Let's suppose this is another one. Let's suppose this is one center, this is another center. Let's suppose radius is given to you r, this one is also r. Clear? Clear? This is r and this one is r. Clear? So now when I am talking about distance, total distance, that is equal to 2r center to center. Clear? So potential energy can be written as k q1 q2 divide by, now I can say instead of r I will write that is 2r. Clear? So now what is value of k? K charge, I am saying this is equal to 1.6 into 10 to the power minus 19 coulomb, and it is divided by 2r. Clear? So what is value of k? Value of k we have, that is 9 into 10 to the power 9. It is multiplied with, what about charge of an electron? So this should be 1.6 into 10 to the power minus 19 into 1.6 into 10 to the power minus 19, and it is divided by, now 2 multiply, what about r? R definitely we have, that is 2 Fermi. So 2 into 10 to the power minus 15 meter. Clear? So now if you solve it, definitely you can get your answer. So 9 into 1.6 into 1.6. Now 10 to the power minus 19, 10 to the power minus 19. This is minus 38 and minus 38 and this one. So 10 to the power minus 29. Clear? It is divided by, we can say 4 and 10 to the power minus 15. Clear? Now you can say if you remove this decimal, you can say that is 100. So that is equal to 10 to the power minus 13. So now if you solve it, 10 to the power minus 13, so this is 10 to the power minus 16. Clear? This one we have, that is 4. Clear? So from that one you can write this potential energy. This should be equal to, now 9 multiply 16, 9 multiply 16 multiply 4 multiply, that is equal to 10 to the power minus 16 joule. Clear? So now you can see, if you multiply 16 with 4, that is 64 multiply 9 into 10 to the power minus 16. Clear? So now if we multiply 64 with 9, so now we can say that is 9 multiply 4, we have 36, we have 3, 9 multiply 6, that is 54, so that is 57 into 10 to the power minus 16 joule. clear. So 576 into 10 to the power minus 16 joule, clear. So this much amount of energy that I am getting, clear everyone? Yes. So actually you can also find this potential energy in terms of electron volt. How? Actually we know this formula, K E square divided by 2R, clear, but we are getting this energy in joule. Let's suppose if we want to convert this into electron volt, definitely we have to divide with 2R with E, clear, and definitely we will get this value in electron volt, clear. This one and this one cancel out, and definitely now calculation becomes easy. 9 into 10 to the power 9, this is 1.6 into 10 to the power minus 19, and it is divided by, now 2 multiply, that is R. R is what? That is Fermi, clear. So Fermi is given to you, that is 2 Fermi. So 2 into 10 to the power minus 15, and we are getting this answer in electron volt, clear. So now you can see that is 9 multiply 16 divide by, that is 4, that is 10 into 10 to the power minus 15, clear. So now this is 10 to the power minus 10, clear. So from that one you can see that is 10 to the power minus 14. So this is 10 to the power 4, clear. So now you can see that is 4, clear. So we are getting this value, that is 360 kilo electron volt, clear. So like this you can calculate value of potential barrier or potential energy, clear. So I think this question is clear to you. Objective is completed to find potential energy, and this is all about this question. Now student, we are going to discuss question number 13.21. In this question it is given to you, we have to utilize one relation R equal to R naught a to the power 1 by 3, clear, where R naught is a constant and a is a mass number of a nucleus, okay. Now we have to show that nuclear matter density is nearly constant, clear. So listen carefully. If we talk about nuclear density, first of all keep in mind nuclear density and mass density is a different term. Why different? Let us try to understand. Whenever we are talking about density, density is equal to, we can say that is mass per unit volume, clear. This is definitely a mass density. But in terms of nuclei, you know that one atomic mass unit, that is indicated by, that is U. Now let's suppose we have, that is Z, X, A. So we have mass number, that is A, means total number of nucleons we have, that is equal to A. So total mass is given by A multiply, that is U. Yes or no? U is what? One atomic mass unit, means we can say that is this is mass per nucleon, you can say. And let's suppose we have total A, that is the mass number. So total mass we can find A multiply U. Volume, if we are assuming a nuclei is to be spherical one, then it is given by 4 by 3 pi R cube, clear. So from that one we can say this is nuclear density. Nuclear density it is given by, that is A U divided by 4 by 3 pi. Now instead of R, now I will write this relation, that is R naught a to the power 1 by 3. So R naught a to the power 1 by 3, and that is cube, clear. So from that one we can write like this, this is A U divided by 4 by 3 pi, then we can say R naught cube, and it is multiplied with A. So A and A, this one is cancelled out. So from here we can write nuclear density, it is given by 3U divided by 4 pi R naught cube, clear. Actually R naught is a constant, and generally its value you will find near about 1.2 Fermi, clear. So first of all you can see in the term of nuclear density you are cancel out the value, that is A, means you can say nuclear density is independent of mass number, clear everyone. Second thing, if we are talking about, let's suppose gold nucleus, silver nucleus, uranium, if I am talking about any nucleus, but nuclear density value always remains constant. So this is a very important statement, that nuclear density is independent of A, clear. So from that one I can write like this, nuclear density, this should be equal to, now 3U, means we can say U is what? That is 1 AMU, and it is given by, we can say that is, what is value of 1 AMU? You know, that is, yes, 1.67 into 10 to the power minus 27 kilogram, clear, and it is divided by 4 pi, means 4 into 22 by 7 into R naught cube. R naught cube means 1.2 into 10 to the power minus 15 and that is whole cube. Clear? Definitely now we have to solve this expression and we can get value of nuclear density. So 1.67 into 10 to the power minus 27 divided by 4 into 22 by 7 into 1.2 into 1.2 into 1.2 into 10 to the power minus 45. Clear? So now if you solve it, you will find nuclear density value. This will be 2.29 into 10 to the power, that is equal to 17. Clear? Kilogram per meter cube. Now you can see actually nucleus is having a very small space, but what is its density? That is mass per unit volume. It will be very large. Clear? So you can say this nuclear density is independent of mass number. Clear? So this is all about this question. Now dear student, we are going to discuss this question number 13.22. Clear? In this question it is given to you, for the positron emission from a nucleus there is another competing process that is known as electron capture. Clear? Electron from an inner orbit, say the K shell, is captured by nucleus and a neutrino is emitted. Okay. So now we have to show if we can say positron emission is energetically allowed, then electron capture is necessarily allowed but not vice versa. Clear? So now we can say, let us try to understand this question. Actually in this question it is given to you, if you are talking about positron emission. So in the positron emission, let's suppose that if we are allowing this positron emission process is to be energetic, means we are allowing this process. So at that time, if we are talking about another process, that is electron capture, so electron capture is also energetic, we have to prove. Clear? But that vice versa is not correct. Means let's suppose if we are saying that electron capture is an energetic process. Clear? But it is not a compulsory condition that you will find this that is positron emission is to be a that is energetic process. Now let us try to understand with the help of some mathematics, then you will get some clarity. Clear? So first I am going to write that is the nuclei equation for the positron. So now you know, that is we know ZXA. From ZXA, let's suppose a positron is emitting, means definitely there will be decrease in a atomic number by 1, so that is X. Now you can say definitely element will change, nuclei will change, so it will be Y. Clear? So this is equal to Y. Clear? So ZXA, it is converting Z minus 1 YA plus, now you can say plus 1 E0. Clear? Definitely with the positron a neutrino particle is also emitting, plus let's suppose that energy that is released equal to Q1. Clear? So from here can we find value of Q1? Yes, because we can decide energetically allowed or not only by the value of Q1. Clear? So now you can say Q1, it will be given by mass defect multiplied 931.5 million electron volt. Clear? So how can we write mass defect? Listen very carefully, I am directly writing that equation. Now if I am talking about atomic mass unit of this one. Clear? So that is a mass of this nuclei of ZXA. Clear? Always keep in mind we have to subtract mass of an electron, so minus times of ZMe. Clear? This one, then we are subtracting. Now this is what Z minus 1, so mass of this nuclei of Z minus 1 Y, that is A. Clear? We are subtracting Z minus 1 into E. Yes or no? Z minus 1 into Me. Clear? Then actually we are also subtracting one more thing, this is equal to mass of this positron. Clear to everyone? Yes. So now from here you can say we can write this value of Q1. Yes, in the last always keep in mind, because we are writing value of Q1, so it should be multiplied with C square, or you can say multiplied with 931.5 million electron volt. So value of Q1, now I am writing, this will be directly I am saying mass of this nuclei that is equal to, actually whenever I am writing like this, it means when I already subtracted mass of electron, it means there is no need of this to write this nuclei. Clear? So this nuclei is not needed. Clear? Not needed. Yes. So now from here you can write directly, this will be M, just a minute. Yes. So now from here we can see that is mass of, that is ZXA. Clear? ZXA. Clear? Minus I am writing ZMe minus ZMe, clear, then minus mass of now Z minus 1 Y A, clear, then plus Z minus 1 into Me, clear, minus, or actually this is minus from this one, so minus Me, and we can say that is multiplied with 931.5 million electron volt, clear. So now from here you can see this is minus times of ZMe and that is plus times of ZMe, this one cancel out, minus Me, this is equal to minus twice of Me, clear. So Q1 value that I am getting, this is equal to mZxa, clear, minus m times of J, means this is mass, m means this is not a multiplication, this is mass of this one, mass of Z minus 1 Y, that is A, clear, and minus times of 2 times of Me, clear, and it should be multiplied with 931.5, clear to everyone. Now if you find same Q value for electron capture equation, clear. So for the electron capture, can we write again the same Q1 value, Q2 value? Yes. So we can write like this, this is equal to mass of, we can say directly say first because this is electron, mass of electron plus mass of, now we can say that is given by Zxa, clear, minus, now we can say mass of electron that will be subtracted, clear, now minus this is equal to mass of Z minus 1 Y and that is equal to A, clear, and now plus Z minus 1 and this should be equal to Me, yes or no. Now if you solve it and in the last definitely you will find again 931.5 million electron volt, clear. Now if you subtract, then you can write like this, minus ZMe and plus ZMe that will be cancelled out, minus Me and plus Me it will be cancelled out, so m times of Zxa, clear, minus m times of that is Z minus 1 Y A, clear, and it is multiplied with 931.5 million electron volt, clear everyone. So now you can say if you compare Q1 and Q2, so definitely this mass defect will be more in the case of Q1, clear. It means actually you can say this term is less in the Q1, clear. So directly you can say this mass defect will be more, means we can say this difference we are getting that will be more, clear. So I can say this Q1 is greater than Q2, yes or no, clear, Q1 is greater than Q2. Now let us try to understand this question. In this question it is given to you if beta plus emission is energetically allowed, clear. So beta plus emission is energetically allowed means then electron capture is necessarily allowed. Listen carefully. Now let's suppose if I am saying this Q that is what beta plus, yes. Now let's suppose if I am saying just a minute, you can say this Q1, this one, and definitely this one, yes, actually you can say this Q2 is greater than Q1, pardon me, clear. Here we have that is Q2 and this is Q1, so Q1 we can say that value we have that is Q2 is greater than Q1, clear. Now let's suppose if I am saying Q1 value is positive, means we are allowing this process is to be energetic process, at that time definitely Q2 will be positive, it must, clear. But let us try to understand, if I am saying that Q2 is positive, means I am saying this process is positive, means this process is possible energetically, but there is no guarantee that you will find Q1 value positive, it may be negative, yes or no, it may be 0, clear. So directly you can say yes, directly we can say if we are allowing beta plus emission, at that time you can say an electron capture can be understand it will be energetically allowed, but if only electron capture is allowed, it is not a guaranteed condition that beta plus emission is also energetically possible, clear. So this is all about this question. Now dear student, we are going to discuss this question number 13.23, clear. In this question it is given to you in a periodic table the average atomic mass of magnesium that is given to you 24.312 U, okay. The average value is based on their relative natural abundance on the earth. The three isotopes and their masses are 12 Mg24, 12 Mg25 and 12 Mg26, clear. Now the natural abundance of 12 Mg24 is 78.99% by mass. Now we have to calculate the abundance of other two isotopes. Clear? So first let us try to write all the information at one place. So now you can see, first I am talking about this isotope 12 Mg, that is 24. Clear? It's we can say atomic mass unit, or you can say it's directly you can say it's that is atomic mass. It is given to you 23 point, we can say 98504 U. Clear? And its percentage abundance, that is given to you 78. Percentage abundance we have 78.99%. Clear? Now if I am talking about next isotope we have, that is 12, that is Mg, and this is 25. Clear? So now if I am talking about this that is mass, so that is 24.98584 and this is U. Clear? Now its natural abundance is not given to you, we have to find. So let's suppose we are saying its natural abundance we have, that is X percentage. Clear? Now we have one more isotope, that is 12, that is Mg, and that is 26. Clear? 12 Mg 26, and if I am talking about this, that is what we can say, that is mass. So this will be 25 point, that is 98259, this is U. Clear? And now if I am talking about percentage abundance it is given by, now directly you can say 100 minus 78.99 minus X percentage. Clear? Yes or no? So now if you subtract it, you will find this value, it near about this will be 21.01%. So 21.01 minus X, and this is percentage. Yes or no? Clear? So now average atomic weight, it is given to you, this is equal to 24.312. Clear? 24.312. So can we find value of X and Y? Yes. Clear? So directly I am writing like this, 24.312, this should be equal to, now 23.9850, 23.9850, clear, and that is 4 multiply, now 78.99 plus now 24.9858, 24.98584, clear, then multiplied with X plus, now we have 25.9825, 25 point, that is 98 and that is 259, clear, and it is multiplied with, now we can say 21.01 minus X, 21.01 minus X, clear to you, and it is divided by, now this is divided by, now you can say because percentage abundance we are talking about, definitely it will be 100, clear. So now if you multiplied it, if you multiplied with this one, you can say 2431.2, this should be equal to, now definitely we have to multiply it. So when you multiply, you can say this will be near about 18, that is 94.58, clear, plus, now if you multiply this one, clear, you can write like this. Overall, directly I am telling you what will be the final answer, because calculation you can do, clear. Definitely if the calculation will be lengthy, you can take some approximate calculations, clear. Yes, so directly I am saying finally you will get, that is 2431.2, this should be equal to, clear, and this should be equal to 18, that is 94.58, clear, then we can see plus 548 point, that is 89, clear, and finally you are getting this is equal to minus times of 0.99, this one, yes, actually plus, clear, you are getting this is equal to minus 0.99675x. Let us try to understand from where we get this one, clear. First I multiplied this one, you can multiply this one, then you can multiply this one. So from that one you are getting these two values, and if you add this one and 25 point something and X, you will get this one minus, clear. So finally if you calculate value of x, you are getting this value, this will be equal to minus 9.27 and it is divided by 9.27 divided by minus 0.99 and this is 675, clear. So from that one we are getting value of x, it will be equal to 11.71, clear. We are getting this value 11.71 and this 11.71 we are getting, clear to everyone? Yes. So now we can say this percentage of this isotope that we are getting, this will be 11.71 percentage, clear, 11.71 percentage, and we are also getting the what is the percentage abundance of 12 Mg26. So it will be equal to 21.01 minus directly you can say that is finally you are getting this one 11.71. So 11.71, clear. So you will get this one, this is equal to 9.3%, 9.3%, clear. So percentage abundance of this one we are getting 11.71, this one we are getting 9.31%, clear. So this is all about this question. Now student, we are going to discuss question number 13.24, clear. In this question it is given to you, the neutron separation energy is defined as the energy required to remove a neutron from the nucleus. Now we have to obtain neutron separation energy of the following nuclei, that is 41 calcium and from 27 aluminium from the following given data, clear. So now fully concentrate on a screen. First of all we are finding actually the neutron energy, actually what you understand by neutron separation energy. So definitely we have a nuclei. If we are providing sufficient amount of energy to that nuclei, we can actually separate out a neutron from that parent nuclei, and definitely a daughter nuclei is also formed with the neutron, clear. So let us try to understand with the help of one equation. So first I am going to solve part number 1, and first of all I am writing this equation 20 calcium, that is 41. Now what I am doing, I am providing sufficient amount of energy, let's suppose that is Q1, and from that I am actually extracting one neutron. So 20 calcium 40 plus, now I can say 0 and 1 plus definitely we have, definitely you can see this one, clear. This is sufficient equation. Now you can say if we talk about Q energy, clear. If we talk about Q energy, so first of all we have to calculate mass defect delta M. So how can we calculate? We can write like this, that is M, this is mass of nuclei of first reactant. Reactant we have, that is 20 calcium, that is 41 minus. Now what is mass of this product? So mass of nuclei of 20 calcium, that is 40 minus mass of nuclei, or you can say mass of neutron, clear. Directly you can say mass of neutron, clear everyone? Yes, mass of neutron, this one, clear. Now you can say actually we are writing mass of nuclei, but whatever is given to you, that is atomic mass, clear. So definitely you have to subtract mass of an electron from this atomic mass, after that you will get mass of this nuclei, clear. So directly you can see we have total 20 proton, clear. Here we also have 20 proton, so definitely 20 electrons and 20 electron mass, that will be cancelled out, clear. Or you can directly also write like this, delta M, this should be equal to, now what is this value for 20 calcium 41, so 20 calcium 41, that I am getting 40.962278, so 40.962278, clear. So 40.962278, clear, minus. Now I am talking about mass of this nuclei, or directly you can say 20 calcium 40. So 20 calcium 40 we have 39.962591. So 39.9625, clear, and that is 91, clear to you. So this is minus this one and minus mass of a neutron. Mass of neutron you know, yes, that is equal to minus 1.0082, Clear? We can write it like this. Clear? So this is just value of mass defect. Clear? So this mass defect final value, if you calculate, definitely you can say you will get this value. This is 40.96. Clear? 40.96, and this is also 40.96, but this side we have 8 plus 2, that is 10. So definitely this will come out to be 7. Yes or no? So 40.97 it will have. So definitely we will get mass defect that is negative. Clear? So if you solve it, you will find this value minus of 0.000089. Clear? 0.0089, and that is 77, and this is U. Clear? Atomic mass unit. Now actually this negative sign is indicating what? Negative sign is indicating we have to provide some energy. Clear? We have to provide some energy. This reaction is not energetically possible. Clear? Actually we are providing certain energy from an external source, and after that we can extract out neutron from the parent nuclei. Clear? So now you can see we can write like this: Q value. Q value means I can say that is value of Q1. It should be equal to minus of 0.008977 multiply 931.5, that is million electron volt. Clear? So if you multiply, you can see value of Q1 I am getting, that is equal to minus 8.632, or you can say minus 8.362, minus 8.362, and that is million electron volt. Clear everyone? Now you can say because with this value we have negative, but actually we need nuclear separation energy. Clear? So we can write like this: nuclear separation energy, nuclear separation energy, it is given by plus 8.362, that is million electron volt. Clear? So nuclear separation energy is given by plus 8.362 million electron volt. Clear? So now similarly we can find value of nuclear separation energy for 13 aluminum 27. Clear? So now I am writing this side. Clear? Second one. Clear? This is first one, this is second one. Now if I am saying 13 aluminum 27, so 13 aluminum 27, clear, plus we are providing some energy from external source, that is Q2, and definitely one neutron is coming out. So we can write like this: 13, that is aluminum, this is 26, plus I can say this is 0 and 1. Clear? And now again we have to find, that is mass defect. Clear? So mass defect, how can you write? This is delta M. This should be equal to mass of nuclei of, first of all, that is reactant. So 13 aluminum, that is 27. Clear? Minus now mass of nuclei of, that is this one, 13 aluminum, that is 26. Clear? And then you can write this is mass of neutron. Clear everyone? So now if you place all these values, you can find this delta M value we are getting, that is positive or negative. Clear? So delta M, this will be given by, now you can say we have 13 proton, so definitely 13 electrons we have. So 13 electron, so we will subtract first from atomic mass. From atomic mass, first of all we will minus mass of an electron, so 13 Me we will find. This side we also have 13 Me, so I can say mass of total electrons, it will be cancelled out. Clear? So now I can write this value of delta M. Mass of, we can say atomic mass of this 13 aluminum 27, 13 aluminum 27, it will be given to you, and that is 26.9815. Clear? So 26.98. Clear? 26.98, 1541 minus, now mass of 13 aluminum 26, 13 aluminum 26, this will be equal to minus 25 point, this one 9868, clear, and 895, so 98, that is 986895. Clear? So minus, what is mass of neutron? 1.008, and let's suppose 1.008, that is 6. Clear? Now Now if you solve it, clear, now if you solve it, you will find value of delta m, value of delta m. Now you can see this value you will get minus of 0.0 minus of 0.014019, clear, clear, and you are getting this mass defect in terms of AMU, clear. So now you can say we are getting this mass defect negative. So if I calculate Q2, clear, Q2 equal to delta M multiply 931.5, that is million electron volt, clear. So this delta M we have, that is minus of 0.014019, and it is multiplied with 931.5, that is million electron volt, clear. So now if you solve it, you can find value of Q2, clear, value of Q2 you are getting, that is minus 13.06 million electron volt, clear, value of Q2 you are getting minus 13.06 million electron volt, clear. So now this value we have negative, this negative value means in this equation, in this nuclear equation, energy is not actually coming out, clear, energy is not in a coming out, means we can say whenever you will find Q value positive, it means energy is releasing, but because we are getting this value negative, it means we have to provide some external energy, clear, if we want to extract out one neutron from the parent nuclei, clear. So like this you can solve this problem. So this is all about this question. Now student, we are going to discuss question number 13.25, clear. In this question it is given to you, a source contains 2 phosphorus radionuclides 15p32 and half life is also given to you, that is 14.3 days, and 15p33 half life is given to you 25.3 days, clear. Initially 10% of leakage come from 15p32, how long one must wait until 90% do so, clear. So let us try to understand. Actually this question is related to radioactivity, and now definitely you know one relation, that is very important relation, n equal to n naught multiply 1 by 2 power, that is n, clear, or you can also write like this, this is equal to n naught 1 by 2 power, that is t divided by, that is t half, clear to everyone. Yes, now you can see, let us try to understand this condition, clear. So I can write like this, what is initial number of nuclei, clear, initial number of nuclei of, now this is 15p32, clear, initial number of nuclei 15p32, and let's suppose, because it is given, listen very carefully, it is given initially 10% of decay come from 15p32, clear. It means I can say, let's suppose if I again write, what is initial number of nuclei, that is from 15p33, clear. Listen carefully, in this question it is given that initially only 10% of decay that is coming from this nuclei, yes or no. It means, now let's suppose I am assuming initially the number of nuclei that remains undecayed, that is equal to x for this nuclei. So definitely I can say here we have, that is 9 times of x, yes or no. Why I am writing like this, because 10% of the nuclei that is decayed, clear, if you add both one you can say that is 10 times of x. So 10% of nuclei that is decay from this this one, clear, 10% of nuclei that is decay. So what is the remaining amount of nuclei? So we can say that is equal to 9 times of x, clear. So now it is also given, we have to find actually the total time taken when 90% of nuclei is decayed from this one, clear. So now can I write like this, final number of nuclei from, that is 15p32, clear, final number of nuclei from 15p32, and let's suppose definitely this is what y, clear, and this will now remains only the 10% of total number of nuclei, clear. So now I can see what is final number of nuclei, in, that is 15p, that is 33, clear, and from that we can write that is 9 times of Y. Clear? Because we have 90% of nuclei decayed, so only 10% remaining. So Y plus 9Y, this is equal to total 10Y. So it will be Y. Y is the 10% of total nuclei. Yes or no? Clear? So now if I utilize this equation, listen carefully, this equation, how can we write? In this equation, N represent total number of nuclei undecayed. Clear? And this N naught represents number of nuclei initially. Clear? So now if I place all this value, number of nuclei that remains for this nuclei, so I can say this will yes, so now I can write like this, that is equal to Y. Clear? Y, because we are talking about this nuclei, so Y equal to, initially we have 9x. Clear? And we can say 1 by 2 that is T divided by half life. Half life of this nuclei, it is also given to you 14.3 days. Clear? Let's suppose this is equation number 1. Clear? Now let's suppose I am talking about this one. What is final number of nuclei of this what is the final number of nuclei? So directly I can say that is equal to 9 times of Y, and this should be equal to, initially we have that is X. Clear? So this should be equal to 1 by 2 T divided by, what is half life? Half life is given to you 25.3. Clear? Let's suppose this is equation number 2. Clear? Now if I divide equation number 1 and equation number 2, clear? So I can write like this, 1 by 9, this should be equal to 9, and 1 by 2, that is T divided by 14.3, and we can say that is divided by 1 by 2, and this is T divided by 25.3. Clear? So we can also write it like this, 1 upon 81, this should be equal to, clear? 1 upon 81, this should be equal to, you can say that is 2 to the power T upon 25.3 divided by 2 power T divided by 14 point, and that is equal to 3. Clear? So you can write like this, 81, this should be equal to, clear? Now 2 to the power T divided by 14.3 minus T divided by 25.3. Clear? Yes or no? Yes. So from that one, how can we write? Let's suppose if I am taking log. Clear? So now I can write like this, let's suppose I am taking log base 10, so it will be, that is 9 square. Clear? Log base 10. Clear? And that is 2 power, now this is T upon 14.3 minus T upon 25.3. Clear everyone? So from that one we can write like this, this is equal to 2 log 9. Clear? This should be equal to, now this power is coming outside, T upon 14.3 minus T divided by, that is 25.3. Clear? And this should be equal to log, that is base 10, and this one is 2. Clear? So now you can write like this, what is value of log 9? Clear? You know what is value of log 9? Yes? Or directly I am saying, if you write value of log 9 multiply 2, you will find this value near about 1.980. Clear? 1.980, this should be equal to, now listen carefully, if I am taking LCM we have, that is 14.3 multiply 25.3. So 25.3 minus 14.3, this should be equal to 14, this is multiplied with T. Clear? And what about log 2? Clear? Log 2 value we have, that is based in 0.3010. Clear? So from that one can we write value of 11T? 11T we have 1.980 into 14.3 into 25.3. Clear? And it is divided by 0.3010. Clear? So 1.980 multiply 14.3 25.3 divided by this one. Clear? So now if you solve it, you will find this value. Directly I am writing value of time. Clear? So time period, that is capital T, small t. Clear? So this small t that you are getting, it will be near about 208.5 days. Clear? You can find some approximation like this. You can say let's suppose this one, let's suppose you are taking 0.301. Clear? You can remove this decimal. Clear? After that you can cancel out with the 301. Clear? So directly you can take some approximation and you can find your answer. This will be come out to be near about 208.5 days. Clear to everyone? So like this you can calculate the total time taken by a nuclei when initially 10% of its 10% of nuclei is decayed, but in the last only 10% of nuclei that is remaining. Clear? So like this we can solve this question. Clear? Now student, we are going to discuss question number 13.26. Clear? In this question it is given to you, under certain circumstances a nucleus can decay by emitting a particle more massive than an alpha particle. Okay, consider the following decay process: 88 radium 223, it is now converting into 82 Pb 209 plus 6C14. Clear? Similarly you can see a radium is also breaking into we can say one is the daughter nuclei, another one is alpha particle. So we have to calculate the Q values for these decays and determine that both are energetically allowed or not. So definitely a very simple question here. First of all we will find mass defect, and after the finding mass defect we can calculate that is Q value. Clear? If we are getting Q value positive, it means these reactions are energetically allowed, and if we are getting Q value negative, that one not allowed. Clear? So now concentrate. Now let's suppose first I am talking about first condition in which radium is now converting into a daughter nuclei that is the made up of that is lead. Clear? So first of all I am writing delta M. So you can write like this: mass of nuclei that is 88, that is radium, this is 223 minus, now you can write like this: mass of nuclei of 82 that is Pb, and this is 209, and minus of mass of we can say that is carbon. Clear? This one. Clear? Or you can also write like this: mass of 6C14. Clear? Mass of 6C14. Mass of 6C14. Clear to everyone? So now you can say first of all definitely we have to subtract mass of electron from this the atomic masses of this nuclei. Clear? Or atomic mass of this radium. Clear? So you can say we have total 88 electrons because that will be equal to protons, 82 electrons and 6 electrons. So total we can say mass of an electron, it will be cancelled out. Clear? So now how can we write? Directly we can write like this: delta M. So don't worry, whenever you will find such type of question, the value of this nuclei it will always be given to you. Clear? So now if I am talking about radium, so for the radium we are getting this value, this is near about 223. Clear? 0.01850. Clear? Minus, now if we talk about this 82 Pb 209, we are getting this value 208 point, clear, 98107 minus. Now what about mass of that is 6C14, it will be definitely near about 14. Clear? So it will be 14.00, clear, 14.000324. Clear? Now if you solve it, you will find this mass defect in the term of that is AMU. Clear? So now you can see delta M, this delta M that I am getting, it will be near about 0.034. Clear? 0.034 and 109. Clear? This is mass defect in terms of AMU. Clear? So now we can say if we talk about energy, clear, or you can say that is binding energy or Q value. Clear? Q value is given by delta M multiply 931.5 million electron volt. Clear? 931.5 million electron volt. So now what about delta M? Delta M, it is given to you 0.034109. So 0.034109 multiply 931.5, this is in million electron volt. Clear? So now from this I can see what value of Q value I am getting, it will be near about 31.85 million electron volt. Clear? Now you can say directly, because we are getting this Q value is positive, it means this reaction is energetically possible. Clear to everyone? Now Now if I talk about this second reaction, clear? So for this second reaction we can write like this: 88 radium 223, 88 radium, this is 223, clear? 88 radium 223, now it is converting into 86 Rn 219. So 86 Rn, this is 219, clear? And we can see now an alpha particle is emitted, so 2He4, clear everyone? So from that one we can write, we have to determine both are energetic allowed or not. So again you have to find first of all mass defect. So for the mass defect we can write like this: mass of nuclei of this 88 radium, that is 223, minus, now I will write mass of this nuclei 86 Rn, that is 219, and minus of mass of, we can say directly, for alpha particle, clear? So now if I write about Q value, clear? So Q value we can write like this: this should be equal to delta M multiply 931.5 million electron volt, clear? So what about delta M, clear? Delta M, definitely if you place all these values you can find value of delta M. Now listen carefully: 88 radium 223, so what is its atomic mass? We can see that is 223.01850 minus. Now what about mass of this nuclei? It will be near about 219.00, 219.00, that is 948, minus what about alpha particle mass? So it will be 4.00, 4.00260, clear? And now you can see we can convert this. If you multiply with 931.5 you can find this answer in million electron volt, clear? So from that one if you calculate value of this Q value you will get, that is 5.98 million electron volt, clear? 5.98 million electron volt. So definitely you can say in both the equation you are getting this Q value positive. It means both reactions are energetically possible and both are allowed, clear? So now we can say this is all about this question. Now student, we are going to discuss question number 13.27, and in this question it is given to you: consider the fission of 92 uranium 238 by fast neutron. In one fission event, no neutrons are emitted and the final end products after the beta decay of primary fragments are 58 Ce140 and 44 Ru99. Calculate Q for this fission process and the relevant atomic and particle masses are this one, clear? Now let us try to understand how can we solve this problem. Actually it is given this fission process is actually started by fast neutrons. So how can we write this equation? 92 uranium, clear, and 92, that is uranium, and we can say that is 238 plus now 0 and 1, clear? 92 uranium 238 plus 0 and 1, and now from this one the thing that is forming 58 C140 plus that is 44 Ru, this is 99, clear? 99 plus definitely a beta particle is also emitting. So beta particle means I can say this is minus 1 E0, clear? Whenever a beta particle is emitting, so definitely some energy is also be released. So let's suppose that I am telling to you that is Q value, clear? So now you can see in this side we have total 92 protons. So if you add 8 4, that is 2, and we can say 1, so total we have 102 proton. It means definitely if we balance this equation we have total 10 beta particles. Yes or no? Yes or no? Clear? So now you can see if we find that, calculate the Q value for this fission process, definitely we will calculate first, that is the mass defect, clear? How can we write this mass defect? So first of all I will write mass of reactant nuclei. So you can say that is parent nuclei. So parent nuclei we have, this is 92 uranium 238, clear, plus mass of neutron minus, clear? Now I will write mass of this nuclei of 58, this is Ce, and 140, clear, minus mass of nuclei mass of nuclei 44, this is Ru, clear, and that is 99, clear, and then mass of that is 10 electrons, clear, mass of we can say that is 10 electrons. So you can say this is 10 times of Me, clear, yes or no, or now we can say this is completed. So this is a formula for mass defect, clear. Now we can place all the values, but before that one you should keep in mind, I will write here first the mass of nuclei. How can we write? Because atomic masses, relevant atomic masses is given to you. So you have to subtract first mass of an electron, clear. So now I can write like this, delta M, it should be, now listen very carefully, clear, that is mass 92 uranium, this is 238, clear, M mass of 92 uranium 238 minus that is 92 electron, 92 mass of electron, 92 mass of electron, clear, clear. Then I can say plus mass of neutron minus, now you can write like this, mass of 58 C 140, clear, minus 58 mass of electron, and then you can say minus of mass that is 44 Ru, 44 Ru, that is 99. Then you can see again you have to subtract that is the electrons. So here you also find that is plus, this is also 44, and we can say that is mass of electron, and now this we are actually subtracting, so I will write this is minus times of 10 Me, clear. Like this you can find total mass defect, clear. Now you can say minus 92 Me, clear. So 58 plus 44, we have 102 Me, and if we subtract 10 1, we are getting plus 92 Me. So this plus 92 Me and this one, it will be cancelled out, yes. So from that one I can write mass defect, it will be given by M, this is 92 uranium 238, clear, then mass of 58 C 140, clear, and then I can see mass of this one 44 Ru, that is 99, and in the last you have that is plus mass of neutron, clear to everyone. Now we can place all the values and we can get this value of mass defect, clear. So from that one if you place all the values, so 92 uranium 238, this value we are getting 238.05079, clear, minus what about this value, we have that is minus 139.90549, clear. Now what about this value of atomic mass, it is given actually in this question, this one, clear. So 98.905, so 98.90594, clear, plus what about mass of neutron, it will be 1.00865, clear, clear. So now if you solve it, you will find this value near about 0.248, clear, 0.248085, and in the last you will write this value, that is AMU. We are calculating this mass in atomic mass unit. Now can we calculate Q value? Yes. So Q value, this one is given by delta M multiply 931.5 million electron volt, clear. So from that one I can write like this, 0.248085 multiply 931.5, this is million electron volt, clear. So from that one can we calculate Q value? Yes, it will be near about 231.09, and this is million electron volt, clear to everyone. So actually the process is very important in this question. If you know process, you can easily solve these questions. Yes, definitely calculation is somewhat tedious, but definitely we have to do some calculation if you want to solve this question, clear. So this is all about this question. Now student, we are going to discuss this question number 13.28, and in this question it is given to you, consider the DT reaction, means deuterium and tritium fusion. 1s2 plus 1s3, this should be converting into twice He4 means in alpha particle and 1 neutron. Now we have to calculate the energy released in million electron volt in this reaction from the given data. Again we have a very similar type of question. So now concentrate. First of all, whenever we want to find the total energy released means we have to calculate Q value, clear, and for Q value we can write like this should be equal to delta M multiply 931.5 million electron volt, clear. So now you can say how can we calculate delta M? Delta M, it can be calculated like this. Now listen very carefully. We have one proton and one proton means total we have 2 electrons. So definitely we have to subtract mass of 2 electron from this atomic masses, clear. Similarly you can say this side we have 2 electrons, so definitely we can say in both sides mass of an electron it will be cancelled out, clear. So directly I am writing this is mass of 1h2 plus mass of 1h3, clear, minus, now directly I can say mass of this alpha particle means twice He4, clear, plus mass of neutron, clear. So from that one we can write like this is minus, clear. So delta M, this delta M, this should be equal to mass of 1h2 it is given to you 2.014102 plus mass of this tritium, so this will be 3.016049 minus, what about mass of alpha particle? Mass of alpha particle it is given to you, we know that is 4 point, this will be 4.00, clear, 4.0026, clear, 4.0026 minus, what about mass of neutron? Mass of neutron we have 1.00862, yes or no, 1.0086, or you can say that is 65, near about, clear. So this is all about delta M. So now if you solve it, definitely you can say if you add it and then if you do subtraction, you will find this value 0.018, 0.01883, clear, 0.01883, and that is 4. So this mass defect that we are getting in AMU, clear everyone? Yes. So now can we find Q value? Yes. So Q value it can be written like this, delta M multiply 931.5 million electron volt, clear. So value of delta M, it will we have 0.0188, 0.0188, clear, and multiplied with 34 multiply 931.5, that is million electron volt, clear. So now if you solve it, you will find this value near about 17.58 million electron volt, clear. So now we can see when this deuterium is actually reacting with tritium and definitely some amount of energy that is releasing, so the amount of energy that released it will be equal to 17.5 million electron volt, clear everyone? Yes. Now we are going to discuss its part number B, clear. In this part it is given to you, we have to consider the radius of both deuterium and tritium to be approximately twice Fermi, means value of R I am taking that is 2 Fermi, so this will be 2 into 10 to the power minus 15 meter, clear. Now we have to calculate what is the kinetic energy needed to overcome the Coulomb repulsion between the two nuclei. So kinetic energy needed to overcome the Coulomb repulsion, so now we can say this is 1 and this one is 2, clear. Now let's suppose I am saying this is deuterium, this is tritium, clear. Now center to center distance it is given to you, that is R, this one is also R, clear. So actually let's suppose initially both are placed at infinity, clear. So when both are coming towards each other, they will exert some repulsive force to each other, so definitely we have to do some external work if we want to bring at a certain position. And in the last, when both touch to each other, can we find its potential energy? Yes, potential energy is given by K Q1 Q2 divided by R, clear. So now you can say what is distance between center to center distance we have, that is twice R, clear. That's why I am writing K Q1 Q2 upon 2R, clear. Now You know what is value of K? Value of K we have, this is equal to 9 into 10 to the power 9 multiply. What about Q1 and Q2? Clear? Q1 and Q2 means now you can say what is total charge. Clear? So total charge, it will be equal to charge of an electron 1.6 into 10 to the power minus 19, that is whole square. Clear? And to multiply. What about R? So R value is given to you, this is twice for me, so 2 into 10 to the power minus 50. Clear? So from that one, if you calculate potential energy, it will be come out to be 5.76 multiply 10 to the power minus of 14 of joule. Clear? It will be 5.76 into 10 to the power minus 14 of joule. Clear? Yes. But actually we have to find what temperature must gas be heated to initiate the reaction. Clear? So if we are talking about what is the energy, kinetic energy per molecule, do you know the formula? Kinetic energy per molecule. So kinetic energy per molecule, it is given by 3 by 2, this is Kb multiply T. Clear? So kinetic energy per molecule, this should be equal to 3 by 2 Kb multiply T. So now from that one we can say what is total kinetic energy? Kinetic energy of two nuclei or two atoms. Clear? So we can write like this, 2 multiply 3 by 2 Kb multiply T, where Kb is Boltzmann constant. Clear? And T is absolute temperature. So it will be equal to 3 times Kb multiply T. Clear? Now you can say this energy, it will be equal to this energy. Clear? So now 3 times of Kb multiply T, this should be equal to 5.76 into 10 to the power minus of 14. Clear? So now I can write like this, 3 into, what about Boltzmann constant? Boltzmann constant we have 1.38 into 10 to the power minus 23. Yes or no? Clear? This is value, and we can see this is temperature T, 5.76 into 10 to the power minus of 14. Clear? So from that one I can write value of capital T. Capital T value we have 5.76 into 10 to the power minus 14 divided by 3 into 1.38 into 10 to the power minus 23. Clear? So from that one, if you are getting final answer, it will be near about 1.39 multiply 10 to the power 9 Kelvin. Clear? Definitely we can solve it. Clear? 10 to the power 23 plus minus 14, so it will be 10 to the power 9, and if you multiply this 3, it will be near about that is 4 point something. Clear? Or we can say 5.76 divided by 4 point something, so we will find this answer 1.39 into 10 to the power 9 Kelvin. Clear everyone? So now in this question you can see the temperature, you can see this much amount of temperature that we needed. Clear? So the temperature that is required if you want to initiate this reaction. Clear? And you will find such high magnitude, such high temperature you will find at the center of sun. Clear? That's why we can say this fusion process is to be taking place in the sun. Clear? So these reactions is taking place in a sun. Clear? So this is all about this question. So student, now we are going to discuss question number 13.29. Clear? In this question it is given to you, we have to obtain the maximum kinetic energy of beta particle and the radiation frequency of gamma decay in the decay scheme as shown in a figure. Okay. Now the atomic masses is given to you for 198 AU and for 198 Hg. Clear to everyone? So now fully concentrate on a screen. Now you can say actually initially we have a parent nuclei, let's suppose that is 79 AU 198, and from that one and another nuclei that is forming, you can say that may be another nuclei, and that is equal to 80 Hg 198. Clear? So initially we can write it like this, let's suppose this is 79, this is AU and 198. Clear? So now from that one actually the another nuclei that is forming 80, this is Hg, and we can say that is 198. Clear? So directly you can say there is no change in a mass number, yes, but definitely we are getting increase in atomic number by 1. Clear? Or you can say there is an increase in the value of Z. clear. So definitely I can see beta minus particle it will be emitted, so minus 1 E, that is 0, and definitely with this one an anti-neutrino particle is also emitted, clear. So from that one, if you want to calculate some amount of energy that is liberated in this nuclear reaction, so I can say definitely first of all we have to calculate this Q value, and for the Q value we need mass defect, clear. So can we calculate first mass defect? Yes, that is given by delta M, clear. So this delta M, it is actually given by like this, mass of reactant minus mass of product, clear. So mass of reactant, now you can say this mass of reactant we have 79, this is AU, and that is 198, clear. This is mass of reactant minus, now I can say mass of product, clear. So mass of product means, now you can say this is actually, we will write here that is nuclear masses, always keep in mind this is nuclear masses 80, this is Hg, and we can say 198, clear. And now I am also subtracting mass of an electron, clear. So now you can say we can also write it like this, delta M, this should be equal to, now atomic mass we have 79 AU, this is 198, clear. Now definitely we have equal number of proton and electron, so definitely you can subtract 79 Me, yes or no? We have to subtract from atomic mass of an electron, clear. After that you will find this is mass of nuclei, clear. Then minus, we can write like this, this is 80 mercury and this is 198, clear. Now I can see we have to subtract total 80 mass of electron, clear. Total we have 80 number of electrons, so we have to subtract masses of electrons, clear. So after that we can also write it like this, this is minus times of Me, clear. Now you can see this minus 79 Me and this minus Me, so total we have minus 80 Me, so minus 80 Me and this 80 Me it will be cancelled out, clear. So from that one we can write this mass defect, it is equal to masses of 79, this is AU, and 198 minus, now we can say this is mass 80, that is mercury, and we can say this is 198. Clear to everyone? Yes. So actually from here if you can place all these two values, you can find value of mass defect, clear. So we can find this delta M, it should be like this, clear. Now what is value of this 79 AU 198? This is 197.96, 197.96, clear. Then 8233 minus, now what is this atomic mass? 197.96, 966, clear. Then 6, that is 760, and now this is atomic mass unit, clear. So now if you solve it, clear, if you solve it you will find this value 0.0014, clear, 0.0014, clear. And you can also write this is 73 and this is atomic unit, clear. Now if you want to calculate total Q value, clear, so Q value is given by, this is equal to delta M multiply 931.5 million electron volt, clear. So now we can place this delta M 0.001473 and it should be multiplied 931.5 million electron volt, clear. So now if you multiply it, you can find this value of, that is Q value, clear. So how can you write this value of Q? This should be equal to, if you multiplied it you will find 1.372, this is million electron volt, clear to everyone? Yes. Now let us try to observe this diagram. From this position to this position, the total energy that will be liberated, that will be equal to 1.372 million electron volt. But if we talk about intermediate states, so in the intermediate state you can see, first of all when this particular nuclei is decaying, a beta minus particle, actually the excited state of mercury that we are getting, and after that we can say the total amount of this one 1.088 million electron volt minus 0. So this much of amount of energy that will be liberating, clear. So first of all I am talking about beta 2 minus, clear. So we can write like this 72, clear. Sorry, this one is 79. we can write like this 79, this is AU, clear, and now I can say that is 198. First of all, it is actually decaying beta minus 2 particles, so beta 2 minus. So at the time actually we are getting excited state of mercury, clear, and after that now you can say from 0.412 minus 0 means we can say 0.412 million electron volt energy that is liberated, and we are getting this nuclei 80 mercury 198, 80 mercury 198. Now you can also see from this one to this one, the total energy that is liberated 1.372 million electron volt. So now if you want to find what is the total amount of energy that will be emitted in this process, can we find? Yes, actually we can find it like this. Now you can say Q value, clear, let's suppose Q dash. So this Q dash, it will be calculated 1.372, clear, minus, now we can say 0.412, clear. So now if you subtract it, you will find this is 0, this one is 6, and we can say that is 9. So 0.960 million electron volt that we are getting, clear. So now you can say this is the we can say maximum kinetic energy that is emitted, maximum kinetic energy that is gained by this beta 2 minus particle, it will be equal to this one, clear. Similarly you can find, let's suppose if I am talking about 79 AU 198, and from that one let's suppose I am taking a beta 1 minus particle, clear, beta 1 minus particle. So from that one we can see we are getting mercury in excited state at this position, clear, yes or no? Actually we are getting this excited state, and from that one again if we are liberating this 1.088 million electron volt energy, so definitely I am getting this mercury as a nuclei, this is stable nuclei, clear. So can we find what is maximum kinetic energy that is gained by this beta 1 particle? Yes. So from that one we can see from this one to this one directly we are getting this, we are getting total energy 1.372 million electron volt, clear. So directly we can find kinetic energy, or you can say maximum kinetic energy of beta 1 minus particle, clear. Maximum kinetic energy, it will be given by 1.372 minus, now we can say 1.088, and now this will be million electron volt, clear. So now if you subtract it, you will find that is equal to 4, now we can say 6, and we can say that is 8, now this one is 2, so 0.284 million electron volt, clear. So this is kinetic energy of beta 1 minus particle, clear. This is maximum kinetic energy, clear. So like this you can calculate maximum kinetic energy, clear. Yes, now we have one more objective, we have to find the total energy, actually the frequency of the photon that is emitted from these energy levels, clear. So first of all let's suppose if I am talking about this gamma 1, clear. So for the gamma 1 actually we know one relation, E is given by that is equal to h nu, clear. You can also write like this, this is h nu divided by E, in this you will find this energy in electron volt, clear. So now if you place value of h, E equal to 6.626 into 10 to the power minus 34 and divided by 1.6 into 10 to the power minus 19 coulomb, clear. So now we can see this value we are getting 4.14 into 10 to the power minus 15, clear, 4.14 into 10 to the power minus 15, and it will be multiplied with nu, clear. Now listen very carefully. First of all, whenever I am talking about this gamma 1 particle, so what is total energy gap that we are getting? 1.088 minus 0. So now I can write like this, delta E1, it should be equal to 4.14 into 10 to the power minus 15, this is frequency that is mu 1, clear. So mu 1, it should be equal to, now I can say 1.088 million electron volt, it means multiplied with 10 to the power 6 divided by 4.14 into 10 to the power minus 15, clear, and definitely you will get this value in hertz, clear. So now if you solve it, you will find this value 2.62, if you solve it you will find 2.62 into 10 to the power 20 hertz, clear. Similarly, you can find this frequency of photon for the gamma 2 also, clear, and for the similarly for gamma 3. So for the gamma 2 we can write it like this, frequency for gamma 2. Now we can see what is energy difference. We have 0.412 million electron volt. So 0.412 into 10 to the power 6 divided by, now I can see 4.14 into 10 to the power minus 15 hertz, clear. So from that one I can get value of this, we can say that is gamma 2, clear. So actually mu 2, clear. Now if you solve it, you will find this value, it will be near about 9 point, we can say that is 9.949 into 10 to the power, this is 19 hertz, clear. Similarly, we can find frequency for the gamma 3 particle. So what is gamma 3? Gamma 3, what is energy give? 1.088 minus 0.412. So 1.088 minus 0.142, clear, 0.412 into 10 to the power 6 divided by 4.14 into 10 to the power minus of 15, clear. Again if you solve it, you will find this value near about 0.1632 into 10 to the power 19 hertz, clear. So like this we can calculate frequency of a photon that is emitted, clear, or frequency of, you can say that is the gamma ray, clear. So finally you can say we have calculated number 1, the maximum kinetic energy emitted by maximum kinetic energy of a beta particle, as well as we can find the radiation frequency of gamma decay, clear to everyone. So now you can see this is all about this question, clear everyone. Now student, we are going to discuss this question number 13.30, clear. In this question it is given to you, calculate and compare the energy released by number way fusion of 1 kilogram of hydrogen deep within the sun, and second one, the fission of 1 kilogram of 235 uranium in a fission reactor, clear. Let us try to understand. Actually there is one popular reaction that you always find. I am first talking about number A part, that 4 times of 1H1, clear, 4 times of 1H1, clear. From that one we are getting, this is actually reaction that takes place within the sun, so twice helium H4, clear, yes or no, as well as now you can say 2 electrons, means you can say the total 2 electrons that is emitted, or you can say beta particle that is emitted, plus as well as total, if we are talking about total energy, so near about 26 million electron volt energy that will be released, clear. So now we can say energy per hydrogen, energy per 1H1, clear, or energy per hydrogen. Now you can say total energy released, this is near about 26 million electron volt. Now it will be divided by 4, clear. So total energy released per hydrogen, it will be given by, this will be near about 6.675, and this one is million electron volt, clear to everyone. Yes, so this is energy per, now we can say per hydrogen, energy per hydrogen, clear. So now from here directly you can say, if we are talking about 1H1, it means in 1 gram we have total number of atoms that will be equal to Avogadro number, clear. So now if I am talking about 1 kilogram, because it is already given in this question 1 kilogram, it means I am talking about 1000 gram. So for the 1000 gram total number of atoms that will be present, Na multiply this is 1000, clear. So from that one we can write like this, 6.023 into 10 to the power 23, it will be multiplied with 10 to the power 3, clear. So from that one we can write like this, 0.23 into 10 to the power 26, and that is atom, clear. Now can we find the total energy released by these number of atoms? Yes. So we can write like this, total energy liberated, total energy released, clear. So total energy released, it will be given by number 1, 6.675 million electron volt, this is energy for per hydrogen. So we can say 6.675 million means 10 to the power 6, clear, and this is in electron volt, clear. Or you can directly write it, because we can find this value is also in million electron volt, clear. So 6.675 multiply, now you can see we have total number of atoms. This is 6.023 into 10 to the power 26. Clear? So now if you multiply, you will get this answer in million electron volt, and it will be near about 40.2. Clear? 40.2 multiply 10 to the power 26 million electron volt. Clear? 40.2 into 10 to the power 26 million electron volt. Clear everyone? Now if I discuss part number B. Clear? So in the part number B, we have to find the total energy released for fission of 1 kilogram of 25 uranium. Clear? So definitely, you know, if we are talking about 92 uranium 235, clear? So the energy released, it will be near about 200 million electron volt. Clear? So directly you can say, because we are talking about 235 gram, so in 235 gram we have total number of atoms that will be equal to near about, that is the Avogadro number. Clear? So if I am talking about 1 gram, so for 1 gram we can write it like this: Na, it will be divided by 235. Clear? Na divide by 235. And now if I am talking about 1 kilogram of uranium, actually this question is very interesting. Why? You will see at the end. So whenever we are talking about 1 kilogram of uranium, the total number of atoms that will be available, Na divided by 235 multiplied with we can say that is 1000. Clear? So Na value we have 6.023 into 10 to the power 23 multiply 10 to the power 3 divided by, now this is 235. Clear? So 6.023 into 10 to the power 23 multiply 10 to the power 3 divided by 235. Clear? So now if you solve it, you will find the total number of atoms that will be available. Yes or no? Or directly we can write like this, because our objective is to find total energy released by 1 kilogram of uranium. So total energy released by 1 kilogram of we can say that is uranium. 1 kilogram of uranium. Clear? So total energy released by 1 kilogram of uranium, and it will be equal to 6.023 into 10 to the power 23 multiply 10 to the power 3 and divided by, this is 235. Clear? And multiply. Now we have this is energy per nuclei of this uranium. Clear? Or you can say per atom. So we can multiply it with 200 and we can get total energy released in terms of million electron volt. Clear? So now from this one we can find total energy release. Clear? So total energy release, it will be given by 5.126. Clear? And it will be multiplied with 10 to the power 26 million electron volt. Clear? Now if we compare total energy released by hydrogen to total energy released by uranium. Clear? Now if you place all these values, so 40.2 into 10 to the power 26 divided by 5.126 into 10 to the power 26. Clear? So from that one you can see this 10 to the power 26 and this one, it will be cancelled out. Clear? And we can get this value near about, you can say 8 times. Clear? So this is very interesting fact. Actually energy released within the sun, you can say this energy will be 8 times of energy released by the same uranium. Clear? It means we know that energy released by one uranium, that will be near about 200 million electron volt. And if you are talking about 1 kilogram of uranium, it will actually release a high amount of energy. But the energy that is released by hydrogen at the center of sun, it will be 8 times of the energy released by, we can say that is uranium. That's why we can say sun is the largest source of energy. Clear to everyone? So like this you can solve this question. Clear everyone? So this is all about this question. Now student, we are going to discuss this question number 13.31. Again a very interesting question, a practical based question. Clear? So concentrate on the screen. Suppose India had a target of producing by 2020 AD, although it is gone, but let's suppose India had a target of producing by 2020 that will be 2 lakh megawatt of electric power. 2 lakh megawatt of electric power, 10% of which was to be obtained from nuclear power plants. Clear? So actually we can say what is the target power. Target power. So target power, it will be given to you, this will be 2 into 10 to the power 6, yes or no, and that is megawatt. So from that one we know what about mega. Mega is actually equal to 10 to the power 6, 2 into 10 to the power 12, that is watt, or you can also write it like this, 2 into 10 to the power 12 joule per second. Clear to everyone? Yes. Now 10% of which was to be obtained from nuclear power plants. So now I can say energy obtained from nuclear power plant. So what is total energy obtained from nuclear power plant? Because only 10% of energy is obtained, so 2 into 10 to the power 12 multiply 10 by 100. Clear? So from that one we can write like this, this will be equal to 2 into 10 to the power 11, and then we can say this is joule. Clear? So 2 into 10 to the power 11 joule of energy that we are getting. Clear to everyone? Yes. Now it is also given, suppose we are giving that on an average the efficiency of utilization of conversion of electric energy of thermal energy produced in a reactor, it will be 25%. Clear? So now we can say actually efficiency of nuclear power plant, that will be 25%. So directly I can say actual energy obtained. Clear? Actual energy obtained, and it will be given by 2 into 10 to the power 11, because the efficiency is total 25%, so directly we can say that is 1 by 4. So 20 divided by 4 into 10 to the power 10. Clear? So from that one we can say this is equal to 5 into 10 to the power 10, and that we are getting, that is joule. Yes or no? Or directly you can say this energy is obtained. Clear? Because directly I am writing this is joule per second, because this time we are not multiplying with the time, or directly you can say this is power obtained. Clear? So actually can we find this energy? This energy is equal to what? That is equal to 5 into 10 to the power 10, and it will be multiplied with time t. Clear? Now if you understand this question, it is given to you what is our objective, how much amount of fissionable uranium would our country need per year. Clear? Per year means, can you say what is the total time? Clear? So total time, now I can write like this, this is 1 year. 1 year means 365 days. In one day we have 24 hours. Clear? And 24 hours 60 minutes, and then we can say this is 60 seconds. Clear? So this is total amount of energy that is liberated, and in terms of joule. Clear? Now listen very carefully. Let's suppose if I am talking about this 92 uranium 235. Clear? So directly we can say in 235 gram, we have total number of atoms, this will be equal to Na. Clear? So now if I am talking about 1 gram, so in 1 gram we have, this is equal to Na divided by 235. Clear? Now if I am talking about 1 kilogram means 1000 gram. So in 1000 gram total number of atoms that will be available, Na upon 235 multiply, that is 1000. Clear? Let's suppose I am saying in 2020 we need m kilogram per year, m kilogram of uranium per year. So total mass of uranium required, that is required, and this will be equal to m divided by 235 multiply 6.023 into, this is 10 to the power 23 and this is 10 to the power 26. Clear? So this we are getting in kilogram. Yes or no? Clear? Now it is also given, if we are talking about energy per fission, so energy per fission we have, that is 200 million electron volt. So now total energy of this mass. Clear? Total energy of this mass, it will be given by capital M divided by 235 multiply 6.023 into 10 to the power 26. Clear? So now we can say this is total energy. Clear? Actually this is mass. Now you have to write this is 200 and multiplied with 10 to the power 6. Now this energy is converted into electron volt. Clear? So now if you multiply it with 1.6 into 10 to the power minus 19, so now this will you are getting in terms of joule. Clear? Now you can say this energy, it should be equated to this energy. clear, and you can easily get value of mass that is consumed per year, clear. So we can write it like this, capital M divided by 235, clear, multiplied with 6.023, clear, multiply 10 to the power 26, multiply, now we can say 2 into 10 to the power 8, clear, and multiply 1.6 into 10 to the power minus of 19, clear. So now if you solve this complete equation from here to this one, clear. So if you solve it, clear, definitely you can solve it. I am writing right answer. This value we have, that is 30, and this one is 761. So 3761, and that is kilogram per year, clear. So like this you can calculate the total mass or the total mass of this uranium that will be required if we want to supply India this much amount of power. Clear to everyone? So this is all about this question. So dear student, this is all about all NCERT and exercise solutions of class 12 chapter, that is nuclei. Clear? So hope you enjoyed this session, and definitely these solutions will be very fruitful for you to understand all NCERT questions as well as to understand this chapter. Clear? So this is all about this chapter. Thank you so much.